So we're now moving on to the next chapter, which is called the amenable group. So the definition of amenability is a really important concept, not only in harmonic analysis on group theory, it's also related to operator algebra, group dynamics, and so on. So I'm pretty sure if you move on to study anything related to group theory later on, you encounter this concept called amenability one way or the other. So let's just start by introducing this concept. Okay, so what's amenable group? So it really dates back to the study of a Norman actually. So if you have a G that's locally compact Hausdorff, let's first define a function. We call it a mean. Okay, so a mean on G is essentially just a linear functional. So let's say M from the L infinity space. So I should use the L infinity big L. To C, so that's a positive, we call it a positive linear functional, or in other words, it's in the dual space of the L infinity space. Here the positivity just really means it maps the positive functions to positive reals. So if you have some f, which is always positive almost everywhere, then the mean of this function is going to be greater than or equal to 0. And also we require that because it's a mean, so it looks like a probability. So the mean of the constant one function is going to be equals to 1. Okay, so that's the definition. So here the second condition sometimes called the unital. So really the mean is a unital positive linear functional on the L infinity space. And I just want to notice one thing. So if you have some f inside the L infinity, you can think about the absolute value of f that's going to be less than or equals to the, well, it's sup norm times the constant 1 function. All right, so the mean of this f, because of this positivity, so it should be monotone whenever your function is real valued and monotone. So this is going to be bounded by the mean of these the scalar multiple of the constant 1 function, but because m is linear, so you can move the infinity norm outside, and you multiply the mean of the constant 1, which is just equals to 1. So automatically you have this kind of inequality. So you can convince yourself the operator norm whenever you have a functional here. Well, technically you don't need to assume it to be continuous in the first place. Well, assuming it's positive and maps the unital and the linear, then the operator norm is going to be equals to 1. So your m is always a continuous linear functional. Okay, so this is just one thing. And so we say a mean is left invariant. So let's say definition. So we say a mean m is left invariant. It just means it's invariant in the left translation. So if I have m of any function in L infinity, that's equals to the m of its left translation. Okay, so Lx of f is just evaluated at x inverse of y. Okay, so this is for all f inside the L infinity of G. Okay, while it's not obvious, there exists a left invariant mean, and in fact, many cases there may not be one. So here's the first definition of amenability. So we say this G is amenable if there exists a left invariant mean. Okay, so if there exists a left invariant mean. Okay, so just the existence of one is suffice for the amenability. All right, so first of all, let's observe a few things. So how can we construct a mean? Well, one way you think about the mean is that you integrate against some probability measure, and that's exactly what happens if your group is compact. So let's observe the following. So if your G is compact, then you just take lambda to be your Har measure. So let's say left Har measure, or because it's compact, so it's really just Har measure. Okay, it's both left and right invariant. And you just consider the functional given by the integral against this lambda. So you let m of f to be the integral of your function f against the lambda. Okay, so that's going to be a positive because your Har measure is positive, and it's going to be unital because your Har measure of the entire group is equal to 1. It's a probability measure, so let's assume lambda G is equal to 1. So this is going to be a left invariant mean. So automatically you have that compact group are automatically amenable. So compact implies amenable. Okay, so that's the first thing you have. Well, not all of these means are going to be coming from these integral against a measure. And in fact, the means are, well, not really the measure. Okay, so we're going to clarify that a little bit first. Let's do one thing. So before we go that, let's observe another thing is that whenever we talk about immutability, oftentimes we only consider discrete groups. So that's the because one thing. So if you consider G with the discrete is if it's immutable. So if it's immutable, then basically there exists a left invariant mean on the L infinity, the little L infinity, because you have the discrete topology on G. Okay, and your big L, suppose G comes with some other locally compact Hausdorff topology, then the big L is going to be contained in the little L of G. And so the constant 1 function on the little L is also the constant 1 in big L. And so if you have a left invariant mean on the little L, it's also a left invariant mean on the big L. So automatically you have that your G is also amenable with whatever topology you begin with. Okay, so it's also amenable. So oftentimes we just look at the discrete group. We try to put a discrete topology on G and see whether it's amenable. If that's amenable, then whatever topology you put there is automatically also amenable. I just want to point out the converse is actually false. So here's the fact. So the converse is false. And so the reason is that, in fact, if you think about some compact groups, compact Lie group even, the SO2 or SU3, those kind of groups, they are going to contain a copy of the free group. And if you ever heard about immutability, in any case, the free group is the first example of a group that's not immutable. We're going to see that shortly. But that only happens in the discrete topology of your SO2 or SU3. Okay, so if SO2, is going to be compact. Okay, so because it's the inverse, the determinant of things in SO2 or SU are going to be positive or negative 1, so they're both compact groups. And so that just shows that the converse is false. Okay, so you can have a compact group which contains some copy of the free group. Okay, but in any case, so in general, when we talk about immutability, we usually only assume the group is discrete. So that's just our assumption. So here's our assumption throughout this chapter. We assume G is discrete, unless stated otherwise, of course, in this chapter. Okay, so let's just always assume the discrete from now on. Okay. So we can forget about the topology. So now, first thing I want to clarify a little bit is this definition of mean. So it's really different from the idea of a measure. So let's think about what happens when you have a mean. So if you have a mean, let's say m is a mean, then you have the m of the first thing you think about is that you consider the characteristic function on some set. Okay, let's assume G is discrete, so this chi of A is going to be in a little L of G. So that defines, you hope it defines some kind of measure. Okay, so you hope, let's call it sigma of A. Well, of course, the sigma really looks like a measure. It has several nice properties. For example, the sigma of the entire space is just mean of the constant 1 function, which is the chi of x, which is 1. So it looks like probability measure. Sigma of any set is going to be greater than or equal to 0. And the only thing that differs from the measure is that if you consider the union of two, so let's say disjoint union of A and B, well, of course, the disjoint union is equals to the m of chi A plus chi B, which is the chi of A union B because they're disjoint. So this is equal to sigma A plus sigma B. So it's finite additive. But if you think about what happens if you try to do it to counter sigma additivity, so if you say this union of AI are going to be disjoint, well, you can do the same trick. Well, this is the m, the mean of the characteristic of the function of the AI. But in L infinity, if you recall, the L infinity norm is basically the soup of all the entries. the summation of the chi AI does not converge to the characteristic function of their countable union, unless all of your tail is going to be the empty set, okay? Because as long as you have one entry that's different, that entry will return a value of 1, so your uniform norm will be 1, so it doesn't converge. Okay, so this is not equals to the summation of the sigma AI. So you don't have the sigma additivity, you only have the finite additivity. So that's in fact where all the mean came from. Okay, so another way of defining the mean is through the following. So if you let sigma from, let's call it from the power set of, let's say, G, technically you don't need to G, it can be defined on any space X. It maps from power set. For each power set, you assign a value between 0 and 1, because we're only talking probability measure. And let's call it a finite additive measure. So I'm saying measure here, but if you remember your measure theory, it's no longer a measure when you only have finite additivity. All right, so if the following thing happens, if it only satisfies the, well, it's a probability measure, so it maps the entire thing to 1, and it only has the finite additivity. So sigma A union B equals to sigma A plus sigma B. If your A intersect B is the empty set, okay? So just recall this is not a measure, okay? So, and you know every mean will give you such a measure, and if it satisfies the sigma additivity, of course it will become a measure on the power set of X or power set of G here, but in general it's not, okay? So, but here's the proposition is quite clear that if you think about all the means, so the set of means on the L infinity, let's use little l because everything is discrete. Let's call it M of G, okay, let's give it a name. That's just equals to the set of all these finite additive measure, okay, the set of finite additive measures, okay. The proof is fairly simple. So we already seen how you go from the mean to the finite additive measure. You just assign sigma of a set to be the measure of the characteristic function. So on the other side, you just basically do the simple function estimation. So you know the simple functions. So simple functions is dense. Let's call it S of G. It's going to be dense in the L infinity of G. That's just some basic measure theory. So what happens is that for every sigma, let's say a finite additive measure, you define a kind of a mean on the simple function. So you define the M naught of your function, let's say summation of some AI, chi of AI, to be the basically what you expect to be. It looks like the integral, so it's AI of the sigma of AI. And you can see that this and not is just, first of all, is well defined, follows from basic measure theory. If you can divide your simple function in several ways, you can always make sure these AI are disjoint, and there's just one way of computing this summation. So basically, you have this M0 is well defined. It's clearly linear. Everything is clearly linear. And this M0, if you think about for every function, let's say h, if you consider its absolute value, so it's going to be less than or equal to the summation of the, let's say this is the function h, the summation of these AI absolute value times the sigma of AI. Well, each of these AI is less than or equals to the sup norm of the h, so less than or equal to the sup norm, and then you sum up all the sigma of AI. And the sum of these sigma AI, that's going to be equal to, well, this is h is a finite sum. So this is eigen from, I should say, eigen from 1 to n. It's always a finite sum for simple functions. So because it's a finite sum, this is the sigma of their union, but the union is going to be a subset of X. And because you have a finite additive, your this finite additive measure is going to be monotone, okay, because monotone doesn't require the sigma additivity. So this one is going to be bounded above by the sigma of X, which is equals to 1. So your M0 is going to be a continuous function from the L, well, the simple function to the complex bounded. This operating norm is bounded by 1. So by the basic function analysis, you can extend it to a linear function on the L infinity. So we can extend M0 to a linear functional on the L infinity of G, and that's going to be a mean. Okay, so this let's extend M to M0 to M inside the L infinity of G, the dual space, and you can clearly see the M of the constant 1 function. Well, because it's the extension of the M0, the constant 1 function is simple, so that maps to 1, and this M is positive, of course. Okay, so that's fairly clear. All right, so this basically clarifies where are these mean came from. Okay, they are a much bigger set compared to the sigma additive measure. Okay, all the measures on G. Okay, they're actually only those finite additive measures. Okay, so as an immediate corollary, so we have another definition of the immutability. So sometimes you see G is immutable. That's just if and only if there exists a finite additive measure, let's say sigma, so that of course is going to be translation invariant. Okay, so the sigma of A is going to be the sigma of G times A. Okay, so as a quick consequence of this characterization that mutability means you have a left invariant finite additive measure, you can actually show that the free group is not immutable. So let's suppose I let this free group generated by two free generator A and B. So if I, for every word, say W of X, okay, to be all the reduced words that start with X, okay, that start with X, okay, so for example, the W of A will be all the reduced word where the first one is A, okay, basically the second you cannot cancel out this A in any way. All right, so you can now divide your F2, the free group, using these reduced words. Well, it's either going to be the empty word, or it has to start with one of these A or A inverse or B or B inverse. Okay, so let's write A inverse, B, and B inverse. Okay, so we divide this F2 into these several ways. Right, so let's suppose this is amenable. So suppose mu is a left invariant and finite additive measure. Okay, so suppose it's amenable. I want to lead to some contradiction. Because it's left invariant, apparently you cannot, the mu of each of these singletons has to be 0. Okay, so the mu of the singleton E has to be 0. Okay, otherwise the mu of each singleton is some non-zero. Of course, it cannot add up to 1. Okay, so that's quite clear. So basically, mu will assign 0 to all the singleton. Well, I just need to care about what mu assign to each of these WA inverse, and so on. Well, one thing nice about the WA is that if you think about what happens to W of A, well, it's essentially every word that's starting with an A. Well, if you remove that A, what happens is that, well, it's basically another element in F2. It cannot be a word that starts with an A inverse. Okay, it can be anything else, but anything but the things in W of A inverse. So this is just equals to the F2 take away W of A inverse. Okay, so if you remove the first element, because the reduced word is A is there, it cannot be reduced any further, and remove it, the rest of it is just F2 take away the W of A inverse. So by the translation invariance, I know the mu of the W of A. That's just equals to the mu of the translation, so I can use the translation invariance, and I say that's mu take away mu of F2 take away of WA inverse. Well, that's just equals to the mu of F2, okay, and minus mu of W of A inverse, okay, that's just by the finite additivity. All right, so the mu of F2, that's being a probability measure, that's 1, and I minus mu of WA inverse. So basically, I know that mu of the WA plus mu of WA inverse, that's going to equals to 1, okay? But I can do the same trick for B, okay? So mu of WB plus mu of the WB inverse, that's also equals to 1. And you probably already seen, well, this is going to lead to a contradiction because the mu of the entire thing F2, on one hand, it has to be equals to 1. On the other hand, it's a union of these 5 disjoint sets. So it's the mu of the identity, which we know is just equal to 0, plus the mu of the each of these 4 sets, which start with A inverse, B inverse. All right, and if 2 of them sum up to 1, the other 2 also sum up to 1. So you end up with the right-hand side is just 2. Okay, that's never going to be equals to 1. Okay, so this is a contradiction. So basically, this shows that the free group cannot have a left invariant finite additive measure, so the free group is not going to be amenable.